logarithms, but now we're going to learn some strange properties. So these rules are going to seem weird at first, okay? But we're always going to relate them back to exponent rules. Molly Meredith, you with me? All right, so in chapter 1, it says that we saw how to multiply powers with the same base, so we added the exponents. So remember when we had like x squared times x to the 5th, we did not say that that was x to the 10th, right? We added the exponents. Does that make sense? So addition, if we add exponents, it's related to multiplication. So I'm going to have x to the 7th here. Well, logarithms are related to exponents, right? We said a logarithm is, by definition, an exponent to which you raise a number to. So if you see something, so a to the m plus n, so if you see something that looks like this, log base b of m times n, it is related to addition. So multiplication is related to addition. So it's going to be log base b of m plus log base b of n. Okay, so students will always get those confused. So they'll start with addition, like they'll go the opposite way. So they'll say things like log base b of m plus n is equal to log base b of m times log base b of n. And that's not true. Okay, so you can only go this one direction. So what I want you guys to do is think about the tens. So if you have log base 10 of 10, let's say, plus log base 10 of 100, think about the tens on this rule if you get stuck on the test. What is log base 10 of 10? Do you guys remember how we did that? Yeah, it's 1. 10 to what power gives you 10, right? That's how we changed that. What's log base 10 of 100? 2. So this should equal 1 plus 2, which is 3, right? So what if I do that multiplication rule? What if I say log base 10 of 10 plus log base 10 of 100, and I multiply these, and I combine it into one log? So I say log base 10 of 10 times 100.
Are you going to, on the test, are you going to expect us to be able to do that?
Yes. So if I have log base 10 of 10 times 100, that's log base 10 of 1,000. Well, what's log base 10 of 1,000? It's 3. So that's a good way for you guys to keep track of what the rule is. So you start with, so if you have log base b of m times n, you write it as two separate logarithms with addition. Okay, so multiplication and addition are related. So if you see something like this next one, log base 6 of 4 plus log base 6 of 9, this would be very hard to do without a calculator if you did not know this rule. Like, I don't know what log base 6 of 4 is. Do you guys know what it is? 6 raised to what power gives you 4? I don't know, right? But if I want to combine these into a single logarithm, I notice that I have a plus in between. So addition is related to multiplication. So when I combine them, I get log base 6 of 4 times 9, which is log base 6 of 36. Now do you guys know it? Yeah, I heard someone say it very quietly. It's 2. Do you guys see why it's 2? Because you're saying 6 raised to what power gives you 36. It has to be 2, right? Does that make sense? Okay, that I did all without a calculator because I knew my rules. Okay, so know these rules. All right, so obviously there's one that goes with division as well, but let's do this one first. So if I have log base 10 of 25 plus log base 10 of 40, I can combine. I can say, oh, I have addition, so I combine them into a single logarithm with multiplication. So 25 times 40. So I get log base 10 of, what's 25 times 40? 1,000. So then I say 10 raised to what power gives me 1,000? 3. Yep, exactly. So that's our answer. I think you guys could do that on a non-calculator test. I think you guys could do it.
Can you only do that when the bases are the same?
Yes, you can only do that when the bases are the same. Otherwise, they're not going to combine.
What do you do if they're not the same?
Then I guess you just have to use another rule. So there's more rules. So there's ways that you can put those in your calculator with different bases, or you could try to change them to the same base. All right, so it says again, when we learned about exponents, we saw that in order to divide powers with the same base, so if we had something like x to the 8th divided by x to the 3rd, do you guys remember what that was? It was x to the 5th, right? We subtracted. So if I have a to the m divided by a to the n, it's a to the m minus n. So subtraction is going to be related to division then. So when we have a single logarithm, with division, so m over n, we can break it into two different logarithms with subtraction. It's going to look like that. So again, we don't know what log base 5 of 100 is because we're saying 5 to some power equals 100, but maybe we can combine these in some way to help us. Okay, so if I have subtraction and I want to combine into a single logarithm, what I do is log base 5 of 100 divided by 4. And 100 divided by 4 is 25. So we're thinking the log is the exponent that we're raising it to. So 5 to what power gives us 25?
2.
Yeah, 2. That's it. Okay, so all of you guys can do this on the non-calculated portion. It's not that bad. There's just a lot of rules with logarithms, so you got to really keep them straight. All right, so the next one, log base 7 of 49 minus log base 7 of 7. This one we could do without combining, right? I could find this and I could say, oh, log base 7 of 49, I know that. That's 2. And log base 7 of 7 is 1, and 2 minus 1 is 1. So you should be able to do these both ways. So the other way would be combining, saying log base 7 of the 49 divided by 7, which is going to be log base 7 of 7. So 7 to what power gives you 7? That's when it's 1, right? So you can do it both ways. It should always work. So I remember when I first started teaching here, so this was a long time ago, I had a student who, she got an A+ on the test for logarithms. She knew her logarithms up and down. And the thing that would impress me is she did almost every single question in a different way. There's lots of ways to solve these, okay? And we'll talk about that when we get to solving equations, that there's probably 3 or 4 different ways of solving a logarithmic equation. Okay, and that's great. If you understand all the different methods, then you totally have that concept down. If you just memorize one way, right, that's okay. You'll do fine on the test if you just memorize one way. But do you really understand how everything's interconnected with logarithms?
How many total methods?
How many what?
Total methods.
A lot. I'll show you a lot of them. All right, so suppose you want to know that log of 3 is 0.477, and log of 2 is 0.301, and log of 7 is 0.845. So I always ask questions like this on the non-calculator portion, and students really struggle with these. Okay, I'm not asking you something that's like rocket science on your calculate or non-calculator section. So I'll show you what students will do, and that's probably when they're like cursing me on their test, like, why would Mrs. Cox do this to me? I won't. I will never do that to you. So if you're doing something crazy, then it's probably not the right method. All right, so if I have log of 6, I want to know how to combine 3, 2, and 7, or just a couple of them, to get 6. 3 times 2, right? So we're going to write that. So we're going to say, well, log of 6, well, that's really log of 3 times 2. And with that rule that we just learned, we know that multiplication, when I have a single logarithm, is related to addition when I separate it. So I'm going to do log of 3 plus log of 2. So can you guys add log of 3, which is 0.477, can you add that to 0.301 without a calculator? Yeah, you can. I know you don't like to anymore now that you have calculators, but we can. We just add straight down. So we get 8, 7, 7, and then the decimal point. So 0.778 is our answer.
I'm confused on how you knew that log of 2 is 0.477.
They're right here. I gave them to you.
Oh, okay.
I wouldn't know that it's 0.477 without a calculator, but... All right, so how about log of 3.5? So think about the numbers we have. We have 3, 2, and 7. How can we combine those numbers to get 3.5?
7 over 2.
Yeah, 7 divided by 2. Did you guys see what Kyle's saying? 7 divided by 2, that's 3.5. So we're going to write it, and we're going to say, okay, well, this is going to be log of 7 divided by 2, which means we break it apart. Whoops, I skipped one, didn't I? We are going to break it apart into log of 7 minus log of 2. I'm on part C. I skipped B on accident. That's fine. So log of 7 minus log of 2 is going to be lining them up. So log of 7 is 845 minus log of 2, which is 0.301. And we subtract, so we're going to have a 4, 4, 5. So 0.554 would be the answer. All without a calculator, we can handle this. All right, so it doesn't matter. We can do B or D. Do you want to go back to B or just do D? We're fine. So if we have log of 12, how do we combine to get 12? 3 times 2 times 2, right? Do you guys see it? 3 times 2 times 2. So we're going to have 3 of them lined up. So we're going to say, okay, well, that's going to be 0.477. And then we're going to have 0.301 and another 0.301. So when we add them together, we have 9, 7, and 10, right? So I'm going to do 0 and then carry the 1 over on the other side of the decimal. So 1.079. So if people don't know the rules, do you know what crazy stuff they do on the test? Every year this happens. And I tell you guys things all the time like this. Every year people do this on the test, and then people still do it on the test. So pay attention when I say things like that. So every year on the test, what people will do is they try to take this number times this number times this number. I don't know why they do it. Do you guys know why they do it? I don't know. So they get crazy stuff, 6 decimals, and then they multiply by another one, and they have 9 total decimals.
How do they do that without a calculator?
It's bad. Please don't do it. Yeah, it's bad. It's bad. So yeah, we should show that sign. We should say plus on that, right? Make sure we show that sign. It's painful. Please don't do it. It makes my heart hurt when I grade, and I'm like, oh my gosh, I can't believe they did this. All right, especially with the division of decimals. Oh, it gets rough. All right, so log of 2 thirds. If I have log of 2 thirds, that's log of 2 minus log of 3. Do you guys see that? So log of 2 is 0.301 minus log of 3 was 0.477. Now this gets a little complicated, and you have to remember some things from elementary school. So think about regular numbers. If I had 5 minus 12, what we're really doing in our head is 12 minus 5, and we're changing the sign, right? That's what we're going to do here. So we're going to do 0.477 minus 0.301, and then we're going to change the sign in the end. Okay, so when we do that, I thought I had already done that at some point. So I get 6, 7, 1. So your answer is negative 0.176. Okay, so does this all make sense? Okay, so the next part says, suppose you have log of 10 cubed. Kind of ran into my thing here, didn't I? So this is really log of 10 times 10 times 10. Okay, so if we have log of 10 times 10 times 10, when we separate it, do you guys see how that's just going to be log of 10 plus log of 10 plus log of 10? We're going to have it 3 times. So here's a new rule for logarithms. So if we had log of 10 cubed, since we can break it up and say, oh, it's log of 10 plus log of 10 plus log of 10, it ends up being 3 times the log of 10. Right? Because if I have something added to itself 3 times, like x plus x plus x would be 3x. Right? So we have 3 times log of 10. That's a weird rule. So if I have something like log of 8 to the 5th, here's what it's having us do. The rule is that really we can kind of just pull that exponent to the front. It's the same as 5 of the log of 8s. Because it would be log of 8 times 8 times 8 times 8 times 8, which is log of 8 plus log of 8 plus log of 8 plus log of 8 plus log of 8, which is 5 of the log of 8s. Do you guys understand that concept? So if you have a logarithm, you can actually take your exponent and you can pull it to the front. Weird, isn't it? We can't do that in normal math. Some calculators will let you, some don't. I'll show you. All right, so it says the logarithm of a power is the product of the exponent and the logarithm of the base. So if we have log base b of m to the c, that c gets pulled to the front. So it's going to be c times log base b of m. So if you have trouble memorizing things, I would put these on note cards, like some of these weird rules, because they're strange at first when you first use them. So when you see something like log base 2 of 32 to the 6th, you don't have to find 32 to the 6th. I don't want to find 32 to the 6th, especially if it's on the non-calculator portion. How do we do that, right? That would be painful. So we're going to take that exponent to the front. So we're going to rewrite it, and it's going to be 6 times log base 2 of 32. And then this part, the log base 2 of 32, we can do. Luke, do you know log base 2 of 32? Yep, it's 5. 2 to what power gives you 32? Does that make sense? Do you guys see it? So we're going to say 6 times 5. So our total answer is 30. So if you need to see this off to the side, some of you guys may not be able to do that in your head. You can always set it equal to x like we did the other day and say 2 to the x equals 32, and then think through. You can say, well, 2 squared is 4, 2 cubed is 8, and you can go bigger, bigger, bigger. But it's 5.
Oh, that was 6.
This was 5 here. X equals 5. So you can do it like 2 times 2 times 2 times 2 times 2. So you have 2 times 2 is 4, 8, 16, 32. All right, so next one. So I'm going to pull the 20 to the front. So we're going to have 20 times log base 8 of 64. So Chris, what's log base 8 of 64? You can do that one. So you're saying what power do you raise 8 to in order to get 64?
I can't put the base on the calculator.
You don't have to use your calculator. You can do it in your head.
Oh,
So if you have,
would that just be 2?
yeah, it's 2. Does that make sense? So you have 20 times 2, which is 40. Yeah, don't overthink things. All right, so this one's a little bit harder. So we pull the 10 to the front, and then we have log base 16 of 4. So don't say 2 on this one. Yeah, it's 1/2. 16 to what power gives you 4? It's a 1/2 power, the square root of 16, right? So it's 10 times 1/2, which ends up being 5. So again, if you need to see that off to the side, you can say log base 16 of 4 equals x. 16 to the x equals 4. X equals 1/2, right? Because it's the square root of 16. All right, so the last one. Can you guys do this? Try it along with me. So how about log base 27 of 3? I think Anna Catherine got this. Log base 27 of 3, what's that part? 1 what? 1/3. Do you guys see it? The cube root of 27 is what gives you 3. And then times 6. So I heard her say 2. She got 2 right away. Does this make sense? All right, so let's try one more rule. So it says we know that logarithms and exponents, they're inverse functions. Just like multiplication and division are inverse functions, or addition and subtraction, inverse functions. So they undo each other. So when we have a combination of like log base 6 of 6, that's going to be something strange. So if I have log base b of b raised to the x, this x goes down to the front, and we get x times log base b of b. Well, what's log base b of b? It's 1, right? So if we had pulled that x to the front and then had times 1, it's all just x. So when you see something like log base 7 of 7 to the 60, that's all just 60. Because the 60 gets pulled to the front, and log base 7 of 7 is 1. Okay, so this other one's a little bit stranger. I can show you why this is true if you guys want to know. But basically, you have something like b to the log base b of x. That all equals x as well. Because the b and the log base b, just like before, they kind of get rid of each other. Yeah. So that one's harder to see why that's true. If you switch it to its other form, I think it makes complete sense. So don't write this, but look up here. Do you guys remember how to switch things around? So like if I had b to the y equals x, we know that that's log base b of x is equal to y, right?
If I put in 60 log base 1, I get
log of 1 is, it's not a base, log of 1 is 0. So if I switch this one around into logarithmic form, we're going to have log base b of x equals that power. Well, the power was log base b of x. Do you see how that's a true statement? Like log base b of x is, says, look from here, b raised to this whole side. Do you guys see it? So if I'm switching around from the different forms, b to the log base b of x equals this spot right here, x. That's what that original equation was. Do you guys see where it's coming from now? Okay, we don't like to switch things around on that one though. So if you see something, so I'll give you another example. So if you see something and you're like, oh, it says that I have 11 to the log base 11 of 3. You know what that is? It's 3. So the 11 and the log base 11 kind of cancel each other out. So they're inverse properties. Oh, I didn't even have, I had 3 and 11 in my head. Look at this next one. Log base 3 of 3 to the 11. So what do we think this answer is going to be? 11, yeah. So that 11 is going to go to the front, and log base 3 and 3 cancel. So this one we could rewrite, and we could think of it in another form. We could say, oh, 81 is 3 to the 4th, right? So that's why what we've been doing, we're saying, what exponent do I raise 3 to in order to get 81? That's why this is all equal to 4. How about number 3? It's a quick one. 10. It's just 10. The 5 and the log base 5 go away. So this next one, 2x minus 1. You can start thinking how 81 is related to 3. It ends up being 3 times 3 times 3 times 3. All right, so number 5. 5 raised to what power gives you 125? 3. 5 times 5 is 25, times another 5 is 125. And then this last one is that rule again. 7. 10 and the log base 10 cancel. Do you guys see them? All right, is that the end? I got more. All right. I think we're probably going to have to stop here, but let me do your homework and I'll tell you where you can go to.